We can now move on to the Q&A portion. Everyone, we do have some questions in already, but if you want to submit a question, please use the question and answer feature rather than the chat. So let's get started with our first question. Last week's speaker stated a preference for V probes. Have you tried the V probes, and can you speak on why you prefer the S probes?
So we do actually have a large selection of V probes in the lab. They're typically used for cortical non-cerebellar recordings. As I said, we really are sticking with the S probes for recording from the flocculus, and really I would stick with the S probes if you were recording anywhere in the cerebellum, since you have to make it past that bilayer of dura. You know, I would say that I have a preference for the S probes pretty much regardless, only because it gives you that sort of extra security factor. It gives you that extra fluffy feeling after inserting your probe through the dura, even if you're only doing cortical recordings. And so I don't really see a downside to going with those stainless steel tips as opposed to the non-stainless steel version. You know, it would just make me feel better, even though I'm not penetrating the dura, say if you're using a cortical recording. It's just that extra security. And so I prefer the S probes, but you know, that's sort of up to the user and sort of laying out their requirements for where they're recording.
Perfect, thank you. The next question, you mentioned using the probes for many penetrations. What method do you use for cleaning the probe between each use? And do you see any changes to the recorded signal over time?
So, you know, that's a great question. So as I said, really, we haven't reached the end of the lifespan on any of these probes that we have. And, you know, a lot of that is careful maintenance. And then again, just the experimenter being careful with the actual probe. Really, any breakage that we see, lost contacts, things like that, they're really user error, not a failure of the probes. So as far as cleaning goes, basically these are acute recordings, so we're inserting them every day. After a recording session, we rinse them with sterile water, and then we soak them in Tergzyme for about 30 minutes. Before letting them dry. And then the next day, just a little bit of brief alcohol, and then getting the alcohol off with some more sterile water before we reinsert it. And we actually haven't seen a significant degradation in the quality of the signals over the course of time. That's sort of the nice thing about having laminar contacts that are on the side of your probe instead of on the tip of your probe, as a conventional electrode or a tetrode perhaps might be, because you're not driving through those contacts. So the impedance, and while we haven't really measured it quantitatively, the impedance, we haven't really noticed a substantial difference in the quality of the signal. They're sitting on the side of the contacts. You don't have a whole lot of things scraping against it, which is also really an advantage for recording in the cerebellum, because again, you're going through that layer of dura, whereas if you go through that layer of dura with a conventional electrode, you know, you're poking that dura with the thing you're recording. And so in a conventional electrode, you would see a pretty sharp impedance drop as you cross the tentorium, which is not the case with these S probes, because you're driving in with something that is not recording.
Great. Our next question, how do you prevent the probe from bending when you attach the plug to the head stage?
So it's a lot easier with the pigtail connectors, in my opinion, than with the head stage that's or with the gain 1 amp that's sitting on the standard probe. And basically all we do is we sort of hang that little pigtail over the back of our micro drive, and then it's just sitting there. There's really no additional stress on the probe. So really nothing bends. And if you want to be really careful about it, we have taped it down. And you know, once you drive the electrode to basically where you're going, we'll then sort of tape everything down, because we're not going very much farther with the micro drive, making sure we leave a little slack before plugging that head stage in. So in a general sense, it's sort of optimizing your the method that you use to put things in to make sure you're never sort of putting additional strain on the probe. And I will say, just because I found it out when talking to the Plexon guys earlier this week, that I would suggest that people, if they're going to invest in probes like these, order some test probes. Apparently you can buy them without any contacts. So you can sort of, break something that's non-expensive that you're not going to, worry about losing. So you can figure out how to handle these things, how to clean them, how to set them up on a daily basis. And I'm sure the Plexon guys can help you with that.
Great, thank you. Next question. Are your unit recordings stable over time? A head-fixed monkey can still move their body in the chair. I would expect large body movements involving the neck could cause movements to the brainstem and cerebellum.
So we do let the probe settle after reaching our target area. And so there is a time constant of movement basically after you've driven things in, which is sort of nice if you have spike sorting software where you can track neurons basically across channels. I know KiloSort does it. We have an in-house sorter that does it. You'll see that the neurons, if you start recording the instant that you get down there, you'll see that the neurons start to shift up the channel contacts. But the time constant of that is usually, anywhere from 15 to 20 minutes. So you sit there for a little while, and then things are basically stable. With regards to overt movements that are still happening while the animal is head fixed, I would say that we don't see that. But to be fair, our animals almost never strain while head fixed. So they're trained incredibly well. They're quite comfortable sitting there for several hours. So they're not sitting there, sort of straining or moving their neck musculature on a regular basis. So we haven't seen it, and it's possible that you would get artifacts from that. But because our animals really don't do that, they're well acclimated to our chairs for months on end. We don't typically see transients like that. Our signals after that initial period of waiting are really quite stable.
Thank you. I think you may have already addressed this, but is the Headstage connector at the end of the pigtail held by something? I'm assuming it's not free floating. If it is, did Plexon make that, or did the lab put it together?
So you're correct. It's sort of free floating there. So the pigtail end is really just to get that connector out of the way, and you can basically sort of hang that any way that you want. One way we've done it is put it over the back of the micro drive. There's screws there. We just really throw it over the back. There's no concern about it pulling on the probe. These things are. It may look big in that picture because I took it close up, but these things are quite small there, and they're not heavy. So you're really not putting a whole ton of strain on the probe at all. And then second, if you want to, and we've done it in the past and it works completely fine, is basically you have your wire that connects to your digi-amp, and you can tape that to the chair or anywhere that you want, so that it's sort of free hanging down. And really movement of that wire, as long as it's not causing additional movement of the probe, doesn't cause any change in the quality of the signal. So even if it's free hanging there and sort of wiggling back and forth a little bit, that's totally acceptable from the standpoint of the quality of the recordings.
Perfect. One attendee asks, I'm considering the use of these types of probes to record chronically from awake behaving NHP thalamus. Have you conducted any chronic recordings with these probes?
We have not. We typically do acute. So unfortunately, I can't speak to that. So yeah, pretty much everything that we're doing right now is acute.
Okay. Next question. When puncturing the dura with the S probe, was a guide tube used?
So we use a guide tube to basically go down to the level of the tentorium. So our goal is to never poke through the tentorium with the guide tube. So we use the guide tube, we go down basically to just above the tentorium. And then we drive the S probe through the tentorium. The benefit being is that you have that S probe sort of wrapped around you have your guide tube wrapped around your S probe, really providing it with additional stabilization, and then you drive it through the tentorium. And really, you only have to do that, if you're going back to the same or a similar area, you really only have to do that once, because hopefully you're accurate enough that you're going through basically the same hole in the tentorium for multiple sessions in a row. So the answer is yes, we do use a guide tube, and we basically go down to the level of the tentorium and then pierce it with the S probe.
Great. Another attendee asks, one aspect of the spike classifier I wonder about, if impedance properties of the probes vary from probe to probe, the classifier might not generalize across probes or even recording sites. So how much variability is there from probe
Yeah,
to
that's
probe?
an excellent question. So we actually haven't noticed a substantial amount of change from probe to probe. Granted, in fact, almost all of the recordings that I showed you today were from the 8.5 micron tungsten contacts. But as I noted before, we haven't really noticed any change in impedance, and therefore the waveforms remain roughly the same. I think that while it's true that the impedance can really change your waveform because it acts like basically a low pass or a band pass filter that's sitting on your waveforms, we try to minimize that by recording only wideband data and then sort of filtering it in a manner that's hopefully agnostic to the impedance of the electrode. But it is a completely fair point. And to really answer your question is, we don't know. And we sort of hope to use mouse optogenetics to start to answer those sorts of questions. Make sure that, use some ground truth data to validate our assumptions.
Great. That same attendee wanted to note, bravo on the possible ability to get data from granule cells. So.
Thank you. We really hope that I hope they are granule cells. They look like granule cells, but I hope they are granule cells.
Perfect. Okay, next question. Does channel impedance play a role in your recording? Do you use a device a la Nano-Z to measure
we don't use the Nano-Z, and in fact, we haven't typically been measuring our probe impedance, but that's really only because we haven't noticed any degradation in the signal. It would be fantastic to measure it. It's just not something that we do right now.
Okay, next question. I imagine the pigtail component of the probe is analog. Does this introduce noise into the system you didn't have beforehand? In your example granule cell burst, it appeared as if the voltage noise floor increased. Is that true, and can you explain it?
Ooh, good question. Let's take a look at my example. Yeah, well, so again, so I think what the individual is asking is, there's some transient DC change. Again, that's a function of your filtering, and in that case, the filters are pretty much wide open. So you're seeing a DC shift only because the LFP is going to change a little bit because of this massive change in spiking. And so that low frequency change is real, but obviously depends. The magnitude of it depends on how you're filtering that signal, and the signal that I was showing you was pretty much wide open, not a whole ton of bandpass filtering going on. I don't believe that it has anything to do with the pigtail head stage. We were concerned, and Damon was concerned about that as well when we first requested the pigtail head stage, whether or not that would increase additional noise in the system. And to be honest, direct comparison of the 16 channel versus the 32 channel, which one has the pigtail, one doesn't, really showed no quantitative difference in the SNR of the signals. But I will say that you're not going and recording simultaneously in exactly the same brain region. So you're sitting there sort of, if you're doing brain to brain comparisons, we don't really have an answer for that. They look pretty much comparable. We could certainly do saline-based recordings to see if the background SNR has changed sufficiently. or changes due to the pigtail connector. But to be honest, the SNR of the signals that we're collecting are fine for our purposes. And so even if the pigtail resulted in, a tiny amount of more noise, to us, it doesn't really make a huge difference because we're still getting great unit isolation. And I will say that, one of the reasons we went to this pigtail is that when we do single electrode recordings, we have the identical length, sort of two wire pigtail, a ground wire and the wire to the electrode, and they're equivalently, a couple of centimeters long. So and we feel that those signal electrode recordings, their quality is acceptable, and so really it was sort of a no-brainer to ask for the pigtail.
Great. So we did just hit 11. David, if you would like to continue answering questions, we definitely can do that. It's really up to you what you want to do.
I'm happy to continue. People are welcome to certainly leave. I'm just sitting here. So I'm happy to answer if people want answers.
Let's keep going then. We have quite a few more questions.
Oh, fantastic.
Next question, have you compared your stereo configuration to linear configuration, and does the stereo configuration confer an advantage in terms of sorting?
We haven't compared it to a linear configuration. That's an excellent question. So we haven't compared it to a linear one just because we haven't ordered a linear probe, and they're a little pricey. Chances are actually a linear would be fine. The bizarre thing, I don't know if it's the flocculus in particular, I imagine it is, but you rarely get substantial voltage deviations. And I should say, I say rarely because it's certainly not never, across the two columns of contacts. Much more often, and I don't know if it's the angle that we're recording, we see neurons that span in axis in each column rather than across axes. If you do get things across axes, that's obviously great. It does provide additional information for your spike sorter to start to separate things. But I will say that that is not the norm. The norm is that we see changes going, or we see neurons going up the contacts, really almost never across, unless you have a very large cell like a Purkinje cell.
Okay, thank you. Next question, what sorting algorithm do you use?
Oh, excellent question. We do not use kilosort. You could, and in fact, it's a reasonable sorter, although the cerebellum is interesting in terms of the background firing rates of these neurons is very high, certainly higher than it is from most places in cortex. And so one of the things that ends up happening, especially on these linear electrodes, is that you get significant collisions between neural units. And so actually we've developed a sorter in-house, Nathan Hall sort of being the lead on that. There's a paper posted on bioarchives, Hall and Lisberger, that I would encourage you to look up. And so basically right now we're using our own in-house software really to make sure that we're getting accurate sorts from these collisions, these overlapping spikes that are happening temporally in time.
Thank you. Next question. Your motor learning tasks always include sensory stimuli. Aren't you really studying sensory motor learning? What role does sensory stimuli have in your recordings?
Yeah, so we are, and I should say, it's sensory motor because it's stimulus driven, absolutely. And so, if you want to find and replace motor learning with sensory motor learning in my talk, you're certainly welcome to do so. The key here is that our sensory stimuli are pretty basic. They're a dot on a dark screen. And so when we try to assay learning, how much learning occurs, we're doing that in probe trials where the sensory stimuli are, as best as we can control them, the same. So the inputs are hopefully the same. Hopefully, the inputs to the cerebellum themselves are the same. And then we're studying the motor learning that goes on top of it due to an error that happened in the past trial. So I think that that's a great question. But the goal is to, at least in the sort of neurophysiology and the behavior we're comparing, we want to make sure that the sensory stimuli of those, in particular probe trials, are as close to the same as possible.
Does the complex spike represent simultaneous firing of multiple neurons?
Good question. In a general sense, no. So it represents the climbing fiber And really it's one climbing fiber per one Purkinje cell. The climbing fiber really sort of invaginates the dendritic growths of these Purkinje cells. And so one climbing fiber response results in one postsynaptic complex spike. And it has these very interesting calcium transients. And so these multiple wavelets that you're seeing are not the fact that multiple neurons are spiking. It's just that that one neuron is firing in a rather interesting pattern. That said, there is a fair amount of controversy, at least in the cerebellar field, whether or not that complex spike is synchronously delivered to a population of Purkinje cells. It certainly must be to about 10 or so Purkinje cells, just because a single climbing fiber branches off and tends to innervate 5 to 10 different Purkinje cells. But how synchronous the complex spikes are across large populations of Purkinje cells, that answer is we don't know, but with linear probes we can start to look at that information.
Thank you. Next question. Do you do Dural scrapes to remove the granulation tissue in your chamber to re-expose dura, or do you drive the S probe through all of that?
Yeah, so we do in a general sense, but not aggressively. And in fact, because we're driving through the dura with a guide tube, we end up sort of mitigating most of that. And again, remember the thing that you're recording from, the things that you're recording from are on the sides of the probe, and you're not actually driving those through that granular tissue. So while we do Dural scrapes, we do them sort of infrequently. We do them sort of the first thing before we start several months of recordings, and then we don't typically do them again after that. But I would, if your granular tissue is really fibrous, our granulation tissue is really fibrous and really hard, then I would certainly get down to the dura first. Anything you can do to minimize the tissue that you're going through is obviously a good thing.
Great. Next question. Have you noticed any difference in field potential signal if you look at LFP at all when decreasing the electrode contact diameter?
We haven't looked at it specifically. That's a good question. We do look at the LFP in pretty low frequency bands, probably lower than most people look at the LFP, just because complex spikes in that Purkinje cell layer result in substantial deviations in very low frequency LFP. And I will say that even with the small diameter tungsten electrodes, the LFP signals that we see that correspond to complex spike activity are quite large. So we're not super filtering those low frequency signals with those high impedance contacts. But that is a concern, I guess, if you're really interested in LFPs. It's not something that we're studying right now, besides using them to really be the hallmark of looking at complex spikes.
Perfect. Next question. Are you computing the autocorrelograms for a specific contact on which the granule cell appears best, or across all the contacts in which the unit is registered? Does the multi-contact probe help essentially in identifying the cell type?
So that's a good question. Except those granule cells, end up appearing only on one contact. So it's unlike most of the other cells that we record on these linear probes. We almost never see a cell that looks like that crossing an electrode boundary, which again is another perhaps piece of evidence to suggest that these might be the small granule cells that we're interested in looking at. So the autocorrelograms are computed basically on the post-processed spike sorted data. And so the spike sorter takes into account spiking across all channels. In this case, there's really only spiking on one channel. So it's an autocorrelogram across all identified spikes happen to be on one channel. But even if it was across multiple channels, the spike sorter that we use basically identifies unique neurons. And so the autocorrelograms that I'm showing are regardless of where the spikes occurred, if the electrode drifted or if the neuron drifted on the electrode contacts.
Okay. Looks like we have one more question. What are the dominant modulatory inputs to the floccular circuit given its proximity to the brainstem?
Yeah, that's an excellent question. So at least in the part of the flocculus that that we're looking at, I don't really know the answer to that, and I'm not sure that I could do the answer justice, but there are certainly modulatory inputs. Most of the mossy fiber-based inputs are vestibular in nature and visual signals coming from extrastriate cortex. So that there are inputs, extracerebellum mossy fiber inputs. As for modulatory, I'm not sure I can answer that question. Besides saying the mossy fibers are coming in, they encode visual and in this case vestibular information.
Okay, thank you so much. That is all of our questions for today. Thank you to everyone who attended. And please make sure to catch our next installment of our webinar series next Wednesday at 10 a.m. Central. Dr. Jeremiah Mara will be giving a talk entitled Examining Mesoscopic Scale Networks in the Primate Amygdala Using Linear Electrode Arrays. And we'll catch you all next time. Thank you.
Thanks, David.
Thanks, David.